So as I was telling, when it comes to CD nozzles, there are like various shape, structure and designs. It all depends on the complexity and the mission it is destined for. So you can just have a look over here. It is sharp in the front, and at the back end, it is like having a smooth curvature profile. And this is the hourglass kind of a structure. And this one, the chamber is too small, but the exit is too large. This is one more type of design. So the thing is, it all depends on what type of engine you're focusing on, whether if it's for liquid rocket engine or solid rocket engine, because the nozzle is the one which plays a major role to accelerate the flow by dissipating the pressure and increasing the overall velocity. But it's not like you're just designing a simple curvature profile out of it. You need to follow a certain principle. Okay, when it comes to rocket nozzles, if you focus on designing the surface curvature of the divergent area, that's actually more than enough. Because if you design that, you can manipulate your chamber pressure, the throat Mach number, and the exit Mach number as well. So that's why, to make it simple, we will be focusing on MOC, method of characteristics, to design the rocket nozzle. So now when it comes to MOC, basically it is called as method of characteristics. It is nothing but a bunch of differential equations where you will be plotting a curve profile out of it. When it comes to making a curvature profile, you need to follow certain principle in terms of the convergence section, expansion and straightening. So in the convergence section, it can be designed freehand. Okay, but all you need to do is make sure at the throat there is exact Mach 1. Okay, if there is exact Mach 1, then you can plot your curvature in a such a way with respect to characteristics lines. The green lines you can see, right, those are called characteristics lines. So basically that's the part where the pressure dissipates at a certain angle and the velocity increases. To make sure that this happens smoothly, you need to maintain the expansion zone, because in the nozzle at the divergent curve there are two types. One is expansion area and one is straightening area. So expansion area is the zone where the diffuser mechanism considers over there. That's the part where the pressure drops and velocity increases. But if you keep on expanding it, the pressure drops drastically. Okay. So you might have been assuming that when it comes to pressure drop, over here it is 100%. As it goes outside, it will become 0%. No, absolutely not. It will be somewhere around like 60% or 70% pressure. Just 40 to 30% drop can be observed over there, because you need some sort of a pressure recovery system in order to get a smooth stabilized flow at varying angle of attack or varying atmospheric pressure, because you need to consider the environmental pressure as well. But now, to keep it controlled, so what we do is we apply a straightening zone. This is the part where it helps in controlling the pressure dissipation rate so that you can get the velocity profile even more smoother. So this is all it is about when it comes to MOC. All you need to do is focus on the throat section, focus on the expansion and straightening section, and focus on the divergent section. When it comes to convergent section, it can be done freehand. Okay, these are all the things which can be done freehand. Even when it comes to any sort of dimensions, you can do based on the customer's requirement, or you can do it based on your availability in terms of the fundings, or you can design it based on any specific conditions. It is totally up to you and the constraints available. But the point is, it can be customized. But when it comes to divergent curve, you will have to make sure that it is following the MOC principle. So we will be doing that. So now when it comes to MOC, I'll just show the components which I have designed at my company. So these are all the things when it comes to rocket nozzles and all. Like when it comes to divergent curve, especially when it comes to divergent curve. So we follow the MOC principle. In the MOC principle, when we design it, you'll be getting coordinate points just like an airfoil. You'll be getting a coordinate points only for the divergent curve. Then rest of it, I can do it freehand. I can literally take a pencil and make a random sketch and convert it into 3D. Just randomly, because if I have followed the MOC principle at the divergent curve, no matter whatever changes you do on the top, the thrust will come out based on the expectations itself. Just look over here. This is a smooth nozzle profile, and this is a straight cut section based on MOC principle itself. So the thing is, these are all random designs, but still it produces the exact thrust which was like calculated for. Now we will be doing the same thing when it comes to designing the rocket nozzles. To do that, so we actually follow a set of code which I have generated using ChatGPT. Okay, so when it comes to making any sort of design, let it be turbine blades or like let it be rocket nozzles. So basically, what we do is we first feed in what type of content I am looking for. Content in a sense, in terms of constraints or boundary conditions, in terms of pressure values, the velocity which I want to expect it at the end, the temperature variations, the material of the nozzle, whatever the propulsion system undergoes, I'll be dumping that in the chat GPT. Then I'll be applying also the MOC principle code. I will be sharing a book for you all, which I have made a report on that. I'll show you one thing. So this is the MOC book which I have written. It's hardly just 45 pages. It explains how exactly it works in terms of MOC principle, energy equations, in terms of Prandtl-Meyer equations, area mark relation, all of it. And you have a code at the end where you can design the overall nozzle. Okay. So this is the thing. I'll be sharing it to you all at the end of the session. You can read this. Meanwhile, I'll just show you the code how it looks like. It's a 3-set code. First one is called as MOC, method of characteristics. So most of the things at the bottom are based on the equations which I have applied. I have showed you the Word document, right? This one. This is the whole prompt for the ChatGPT. This was the whole prompt for the ChatGPT where I typed it, and then I have like distinguished it like in terms of area mark relation separate, in terms of Prandtl-Meyer separate, because if you interrelate all of it, then only you can match equilibrium pressure dissipation along with velocity incrementation. So based on that code and based on that prompt, I got a certain set of code like this. But all you need to do is manipulate the input over here. Okay, one thing I want to say, y'all, please don't learn how to code. Okay, so just learn what is necessary. If you start learning everything from the scratch, it is actually a bit time waste, because most of the things can be done something which is available, right? It is done by that. So why do you want to crack your heads on that? Even when it comes to industrial manufacturing, majority of the things we don't learn about it. We directly implement what's available and make some random changes and we get the desired results. So that's why now we are using ChatGPT to generate the particular code. And this is the code which I have got, and I have specifically mentioned that I need to edit the overall throat diameter, the throat Mach number, and the exit diameter and the exit Mach number. So these are the editing options available. This is the input area where you can change your diameter, radius of throat, throat Mach number. These are all the like specific gas constant and heat ratios. And this one is really important, exit Mach number. You can put any number if you want. Suppose if I want exit Mach number to be 2.5, I can get it done. If I want the exit Mach number to be around 4, I can still get it. The overall point of view of this code is that you can give any dimensions and you can ask it what type of Mach number at the exit you require, and it will do the design for you. Next is Prandtl-Meyer equations. So this is the part where basically it's not like the whole pressure dissipates completely during the expansion area. That's the part where you need to make sure the length of the divergent curve is appropriate. If it is too short, it acts like an explosion. If it is too long, then it undergoes choking condition. To keep it equilibrium, we follow Prandtl-Meyer equation. And then area Mach relation. That's the in terms of like the throat area and exit diameter. So based on the input values what you give, we are just gonna relate it. In terms of relation, I'll just copy all the codes, dump it in MATLAB. We will be using MATLAB for designing this. So I actually couldn't no make up with the MATLAB issues. So that's why I will be using MATLAB online. So I'll go to Google search, type MATLAB online, and I'll go over here. So you can actually use MATLAB using your professional mail ID or your college mail ID or your personal mail ID, anything. But you have a limitations of 20 hours per month. Within 20 hours per month, you need to complete any sort of simulations. In terms of learning, it is not feasible. But in terms of executing any sort of codes at a short period of time, that would be quite feasible. So now I'll click on Open MATLAB Basic. See over here, hours used this month. I have used it only for 1.1 out of 20 hours. I went to MATLAB right now. Then I'll be copy pasting the code. Let it load. Okay. So now I have pre-fed the code all over here. So the thing is, assume that nothing is over here. I'll be deleting everything. You need to learn from the scratch like how to do it. So now over here, I'll click on new script, and this is the platform where you dump in the codes. I'll be adding 3. Now in the first one, I'll copy this MOC, Control A, Control C, and I will dump it here. Next is area Mach relation, Prandtl-Meyer. Control A, Control C, and I will dump it here. Okay, I have split the screen so that it will be easy for me. I'll click on new script as I told, add 3 sets. In the first one, Control A, Control C and dump over here, MOC. Second one, go to PM equation. Control A, Control V. And the third one, area Mach relation. That's it. So now, once you are done with this thing, you need to save each file. Okay, like Control S. And here I will save it as method of characteristics. MOC nozzle. Okay, I'm saving it as MOC nozzle and click on save. Over here, this one, Control S, PM equation. Save it. And this one, Control S, AM relation. It is already showing up. I'll click on save. That's it. Till now, it is done. Next in MOC, I'll go to the top completely. In the diameter, I can set any diameter if I want. I can set any radius if I want. I can set any Mach number if I want. I'll just zoom in. In the diameter, I'll keep it somewhere around like 10 centimeter. It's in mm, okay. Anything you can see the percentage wise, it is in mm. I'll be keeping it 100 mm, that is 10 centimeter diameter. It's a small nozzle, small engine, like it is micro category. Not micro, I guess small category. Yeah. Next is radius of throat. I can give it anything if I want. Instead of giving it 50, I'll give it something around like 47, a random number. Okay. These are all based on my constraints. Like if I am working on a project where I want to fit the rocket engine in an existing rocket tube. Okay, so for that, based on the like dimensions, I can give anything if I want. Exit and this thing, the throat Mach number, I'll keep it to exact 1. Next thing is over here in the exit Mach number, like what exactly I want. So over here, I'll keep it as 3.4. I want exit Mach number to be 3.4. That's the nozzle area. You can let it be as it is. Meanwhile, when it comes to precision points, this is numchar, number of characteristics. So the points you can focus on over here, it totally focuses based on the precision in terms of aligning it. In terms of aligning, I'll just run it, okay? It will be easy for you to understand. I'll just run it, you'll get a picture. You'll get a curvature profile. To maintain the precision, you need some sort of points. Over here, you'll get this error, okay? You can find this error, so don't care about it. It doesn't matter. Now, when it comes to pressure values, when you are complete with the design, right? When you're testing it in the ANSYS software, it will tell you what sort of pressure conditions and values you need to put. Look over here at the bottom and command window, like in the past pressure, in terms of temperature, all of it will be given. So you can directly dump it in the ANSYS software. And this is the design. You will get only the divergent curve because that's the important part. You can see this 50 green points, right? I have typed 50, so you have 50 green points. And exit Mach number 3.4. It is given already. And if you want it for 3.5, you can still customize it. Or if you want it for 2.7, 1.1, any Mach number, you can make it happen. Next thing is, if you want to check on the coordinate points, just click on the green dot. You can get the values in terms of x-axis and y-axis. Then you need to make a note of it in Excel sheet to import the coordinate points in the CATIA software. So now 3.4, right? I'll change it to around 2.5. 2.5. Number of characteristics lines, 50 is too much. I'll keep it around like 20. Now I will click on run. See, already the pressure conditions changed again. Okay, now see, 2.4. I mean 2.5 is over here, near to it. You can also edit your dimensions again. Instead of giving it 10 centimeter dia, I'll keep it 70 centimeter. I mean 70 mm dia. That is 7 centimeter. Click on run. The design also slightly changed. The throat became slightly bigger when compared to previous one. So it's a very simple thing. You need to click on the coordinate points individually and make a note of it in the separate Excel column like this, x-axis, y-axis throughout. The thing is, if you are using any sort of MATLAB software, you can directly import the coordinate points. But since I'm using MATLAB online, it has a lot of limitations. So that's why the thing is, see, clicking on each green points and making a note of it is a bit lengthy process. So that's why I have done this ready-made. This is for 2.5 exit Mach number, 5 centimeter, sorry, 5.5 centimeter dia, and 23 mm in terms of throat. So we'll be designing this right now. I'll go to CATIA, click on Start Mechanical and go to Part Design. And here I'll click on XY plane and sketch. Now I'll import the coordinate points. To do that, I'll choose the whole XY coordinate list, Control C, and go to Generative Shape Design, Control V. And the rest of it, I'll keep it as 0. Now this one, Control X and Control V. That's it. Click on Views, Macro, View Macro, Main, Run. Now I will not press 3. I'll keep it as 1 because I will be shaping the diameter as well. I'll be shaping the spline, so I keep it editable. I just want the points, so I click on 1 and OK. Go to CATIA. You can see the coordinate points being dumped, but you still cannot see the coordinate points because you'll have to go to Customize View Parameter and select No Point. That's it. You got the curvature. The reason why you only got the outer curvature because MOC focuses only on the pressure dissipation and the velocity increment. When it comes to the convergent area, that can be done freehand, literally freehand. You can make a straight line, curvy line, or a rectangle, literally anything. All you need to do is make sure throat has exact Mach 1. If you maintain that, you're good to go. I'll show you right now. I'll go for spline. I'll just click on the points and connect it all. I'll just trace it. That's it. If I click each and every point, it will take a lot of time. Instead, just trace it. It follows the path automatically. Now, customize, hide the coordinate points. Now you got the divergent curve. To make the convergent curve, you can take profile tool. You can make something like this. Later you can shaft it. For example, I'll show you. You can make something like this and you can take this line and shaft it for 360 degrees. Or there's one more option. You can take spline tool again, make a smooth profile. That's it. Now, when it comes to the chamber length and the chamber diameter, that is completely customizable. You can do it regardless of any sort of equations. You don't need any equation for designing the convergent area or the chamber length and the combustion chamber length or anything. All you need to do is make sure that over here it is exact Mach 1 and divergent curve should follow MOC principle in terms of curvature. That's it. Now let this design be as it is. It looks pretty good and I will choose profile tool. From here, from the origin center, I'll connect it. Now, when we use this model for simulation in the answers, I will prove it to you that this will produce exact Mach 2.5. You can do for any shape structure, but to just test the code is right or wrong, this is a live example. So just do randomly, but make sure you maintain this. Okay. Exit the workbench. Shaft option for 360 degrees. And now I will choose shell. Choose this face. The thing is, it has option inside thickness, outside thickness. If I give inside thickness, the curvature profile will be disfigured. So that's why to keep it like precise, I'll give outer thickness of 5 mm, internal 0 to maintain the precision. Press OK. Now you have outer wall thickness. Internal wall thickness is with respect to the MOC curve. So now you don't need to worry about the precision. It's all done. I'll go to dynamic section. You might have observed only at the exit I have made a hole, but here I have kept it solid like a face. You know the reason why? Because when I perform the CFD analysis in the answers, if I keep it open, anyways, I need to create an imaginary surface and name it as inlet. So it is a lot of mental gymnastics. So to prevent it, I just directly cover it and name the whole face as inlet. Inlet, in a sense, that's the part where the fuel injection and the combustion takes place, where it pushes the flow outside. So I'll name it as direct inlet, and then you can visualize the high pressure converting to higher velocity. So the transition can be noted down smoothly in the answers tool. To keep it simple, make sure you cover this and keep this end open. Now you can check the weight of it if you want. I'll go to material, I'll keep it as stainless steel, and I'll check the weight. It is 6.952 kgs. Okay, it's a pretty small engine what we worked on. So okay, fine. This is good. So this is how you design the rocket nozzle. Now similarly, I'll go for mechanical and part design. XY plane, go to sketch. We will design something based on opposite of CD nozzle. So now I'll just explain the advantages and disadvantages. Advantages of CD nozzle is that it can produce excessive amount of thrust, which is totally powerful. But in terms of varying atmospheric pressure, there are high chances there will be flow instability within the engine. Okay, the pressure recovery will be too bad as it goes to space conditions. To prevent that, you need to come up with something which concentrate the thrust. We don't want high thrust. We need concentrated thrust and a better specific impulse. That's why we go for one more set of design. It is called as Aerospike nozzle. So it is nothing but the inverse of CD nozzle. This is how it is. You cut the CD nozzle in half and you flip it. It looks like Aerospike. These are all CD nozzle. The curvature is CD nozzle. The rest of it is freehand design. But now over here, you can see a flat bottom, right? You can make sharp bottom, round bottom, or spherical bottom, oval bottom, anything. So just look at the design over here. This will be your inlet, the spike, and this is your outlet. The thing is, it generates quantum mechanism at the surface curvature over here, where it makes the flow to stick towards the convex surface, and as it goes outside, it sticks on the spike. It is aerodynamically efficient, where it generates a lower pressure zone. When it generates lower pressure zone at the spike end, the higher pressure environment area will get sucked in. Since there is a lower pressure zone at the high velocity area, the surrounding air pressure will get sucked in. It mixes along with the flow to concentrate the thrust. So this is the CFD perspective of it. There will be stagnation point. I'll be teaching that in the answers tools later. But the point what I want to convey over here is that Aerospike is known for concentrating the thrust at varying altitudes. So when it comes to design, this is one type. You can go for complete spike, or you can go for flat bottom. There are like various designs and structures that is available. Now, when coming to the point, the flow perspective, you need to understand why I prefer Aerospike, why I prefer CD nozzle. When it comes to flow, there are many types. Okay, optimal, optimal, optimal. Like this is not the thing. The first one, it is called as overexpanded flow. This is for Aerospike and this is for CD nozzle. Overexpanded flow is something where the pressure of the environment is greater than the pressure of the rocket engine. So the pressure of the environment makes the rocket thrust to converge over here. Then it will look like a diamond shock wave. So there will be recirculation happening over here. This is overexpanded flow for Aerospike. Now next is perfect jet flow. That means pressure of the engine is equal to pressure of the environment. Then it comes out like this. This thing cannot be achieved. It can be achieved in CFD simulations, but it cannot be achieved in real life. It's too tough. Next is under expansion. The pressure of the engine is greater when compared to pressure of the environment. That is in space conditions. You know, right? A rocket in the sea level usually produces a thrust which is concentrated, like it will be overexpanded. But if you go to the space conditions, there will be a huge plume that will be shown up. So that is the thing over here. When it comes to Aerospike versus CD nozzle, at space conditions, CD nozzle actually fail because the vacuum will cause flow instability. Eventually, the CD nozzle cannot produce good specific impulse. But when it comes to Aerospike, no matter what, it will somehow concentrate the thrust due to the aerodynamical design of it. So that's why we prefer that. But still, people go for CD nozzle by making some changes. But Aerospike is quite more efficient, but it is very expensive because the maintenance is too high. The problem is that Aerospike undergoes extreme frictional flow, which gives rise to higher entropy and higher temperature. Because you can see the stagnation point now, the blue color is stagnation point. That's the part where the flow vortices suddenly rises, because that's the area the kinetic energy drops and the internal energy will rise. That is nothing but the temperature. Then it wet along the overall body structure. So this is the profile, a divergent curve. This is the divergent curve which I got for the CD nozzle. It will be like this, and then I made a spline like this, a straight line, inlet from the origin axis, made a straight line till here for matching the straight line here, and curvature profile. This is totally random. You can keep it till here or you can keep it till here. It's up to you. Again, straight line. This is the outer covering so that I can shaft it. At the front end, instead of making it spike, I have purposely kept it flat bottom because during the ANSYS simulations, it will be quite interesting to show how the stagnation points will be formed. Then later we can come up with a better design to eliminate it. Now exit the workbench, shaft, that's it. I got the spike. Then dynamic section, this is the curvature which I wanted, and this is the covering area, the casing. This will be your inlet. See, the thing is, when it comes to the design, you can actually make it look good. For example, you just go to sketch. You can go to sketch. So I will try manipulating a design. I'll delete these lines. exit. So I got this thing. It looks pretty weird, but somewhat okay, fine. Now I'll just click on dynamic section. Now I'll just choose this face, go to sketch for making like a flange basically. When it comes to designing, try putting some efforts to make it look good. I'm just doing it randomly just to show how you can manipulate the structure. You can do it completely freehand, but just make sure the outer curvature is maintained. If you do that, then that's all I require. I'll choose circular pattern throughout the circumference. Basically, when you're fitting on the engine jigs and fixtures, you need a flange to hold the overall casing right. Then upon the casing, there will be support structures. Within the support structures, there will be space for the fuel tank and the oxidizer tank. So the design is completely like flexible. You can come up with anything literally. Yeah. So that's it. Now, when it comes to applying the material and checking the weight, it will be literally too heavy because just look at the surface thickness over here. It's too high, right? The reason why we need to keep it too high because just look at the picture over here. It might look thin, but it is too thick. There is a term called as aerothermoelasticity. That means not just unsteady aerodynamics will cause the structural casing to vibrate, but also due to temperature, it literally becomes soft and it tends to move like butter. To prevent that, we go for making it thick, or second option is you can go for a different materials in terms of inconel or stainless steel different series or titanium alloy like that. That will be quite helpful. And when it comes to coolant systems, you can see internally the grooves and structures. So that's the part where liquid nitrogens usually flow around, or any sort of cryogenic unit where it maintains the overall temperature by maintaining a potential difference. You can go for many types for cooling system. For example, for CD nozzle, helical cooling system. So this is the CD nozzle at the back end. Okay, inside there will be grooves like this. Within the groove, there will be like a liquid nitrogen flowing where it maintains the icing, so the temperature can be maintained. This is also one of it. There are like various types for cooling systems. Just like for turbine blade, there will be hole for rocket nozzles. They put ethanol, kerosene, water, other fluids. So, anyways, we are done with today's session. So, this is the Aerospike. It's a pretty simple design, but when it comes to maintaining the precision, it is quite challenging. So, I suggest you all to come up with your own random designs, but make sure the divergent curve is maintained. If you maintain the divergent curve, then it's pretty good for any sort of simulations.